When I was approached by the organizers, I quickly cobbled together a very broad brushstroke, vague abstract, and then lived to regret it when I realized I would have to actually deliver what I promised. I'm going to talk a little bit about organic electronics and some of the principles and some real devices. I've tried to remove most of the maths, and there might be one equation remaining. No, maybe not one, maybe a couple of slides of equations. And then I'll talk about some of the more recent works and work we just had published in January of this year on some detectors. So, organic semiconductor devices exist, and you can buy them. And in fact, the examples I've got here are, if anything, slightly out of date. So LG sell what they call OLED televisions. OLED stands for organic LED, right? Samsung, I mean, you can buy these on the high street. They'll sell you a display, which is a purely emissive organic LED display on a smartphone. Organics are kind of cool because, well, they're plastics really, and so that means that, you know, you can make them fully flexible. And I know that there are even more recent devices that make use of this these kind of capabilities, but they're not only limited to light emitting diodes, and not only limited to displays. You can make a photovoltaic, a solar cell out of them. Here's some photographs of some prototype Merck, as in the chemical company, as in the Emil Merck from Darmstadt kind of Merck. They in fact have a patent on the synthesis of the polythiophene, and so here are some examples of a photovoltaic. So you can use essentially the sunscreens on your glass building to not only stop the sun's glare sort of blinding people working at the desks, but also to generate some useful power. And of course, what we see on the left is e-paper. Okay, this is the electrophoretic type of display that you would have on something like a Kindle, okay, some kind of reader. And although that's not organic, the transistors that drive it are organic. So basically, you can make these organic transistors, and because you can make them, they're extremely thin, they're effectively transparent. Okay, so you can make light emitting diodes, you can make photovoltaics, you can make transistors. You can really do electronics with organics, and you do this commercially. You can, you know, people get jobs doing this for companies. Okay, the Samsung curved televisions that were OLED are organic and fully emissive, and in fact, the curvature was a problem with their production. That some clever person in marketing said, "Oh, that will make that a unique selling point." And there are huge production facilities. I mean, huge. I mean, sort of display facilities, the size, you know, factories, the size of many football pitches. So, okay, we have organic semiconductor devices, and we can buy them, and that's all very nice. What do I mean by organic? Okay, organic means some kind of carbon compound, right? Carbon-containing compound. Organic chemistry is essentially the chemistry of carbon. Okay, and what do I mean by semiconductor? Well, you know, my simple kind of definition of a semiconductor is what? Well, it's something that's got a full valence band and an empty conduction band, and the energy gap is modest. It's electron volt sized. Okay, so we need, out of something organic, to make a semiconductor, and for that we need conjugated bonds. And so on the left I've got my cartoon of what a semiconductor looks like in my very simplistic kind of view, and on the right I've got actually it's polyacetylene, and it's an interesting thing about conjugated bonds. And what do I mean by conjugated bonds? Conjugated bonds are really just alternating single double bonds, right? And the interesting thing about them is we can swap the positions and leave the chemistry unaltered. So that's kind of interesting. So let's think about how we make a covalent bond. So we have an extremely simple molecule, ethylene, and that has this double carbon-carbon bond. And the way we make the double carbon-carbon bond is we take these two pz orbitals, this 2pz, I suppose they're spherical harmonics, right? They're wave functions, if you want. They are the 2pz spherical harmonics, and one from each carbon. And then the bond is just the linear combination of these 2pz electrons. A bond is just two electrons, one spin up, one spin down, sharing a common wave function, and we call these a pi bond. Okay, and so you have sigma bonds, which are formed by the covalent bonding of lower lying energy states, and then the highest energy electrons, these 2pz's, combine, share a wave function, one spin up, one spin down in a common wave function to form these what we call pi bonds. But we can combine wave functions. I mean, here are the two simplest linear combinations I could think of. I take psi1 and add it to psi2 and get a symmetric combination, which we call the bonding one. Or I could take the next simplest solution, is to take the psi1 minus psi2 to make the antisymmetric. Well, minus psi2 just means psi2 out of phase, right, with a phase factor of pi. And so we have a symmetric linear combination, which is called the pi, the bonding combination, which is psi1 plus psi2. And we've got what we term the pi star, because it's higher lying, which is the antisymmetric. So the symmetric is in phase, the antisymmetric is out of phase. Okay, sorry, just got to check something. Yeah, no, that's absolutely fine. I apologize. I'll continue from. Oh, sorry about that. So where was I? So that's nice. So I don't have just one way of combining these two wave functions. I've got two ways. In fact, I've got an infinity of ways, because I could make any kind of linear combination. These are the simplest ones I could do. Now, what we know about linear combinations is that they're energetically different. See, the pi, the symmetric linear combination, has a lower energy than the pi star. And the reason why it's got a lower energy, if you think about it, is because it is a bonding combination. It gives rise. Okay, I know it depends on the parity of the wave function we start off with, but it gives rise, if you want, to a high probability density between the two carbons for the electron, and therefore gives rise to, if you want, an attractive kind of force. So if I look energetically at my energy levels for this for this, even this simple molecule, the ethylene, I'll notice that I've got all these full levels at the bottom. The sigmas are all full and they're all lying down. And then I have the pi level, which is my symmetric bonding combination, and that's full of electrons, right? And then I have these other levels higher up, a pi star. Of course, there's a sigma star even further up. But the interesting thing about it is, if you look at the pi star transition, that's the right size. Okay, so it's electron volt sized transition, which means it is suitable for doing semiconductor devices. It's suitable for doing some electronics. Just like when we said with our traditional semiconductors, we have a full valence band and an anti-conduction band, and the gap is kind of electron volt sized. So you should have all seen that, and I managed to fish out a picture of Paul Dirac looking at exactly the energetics of symmetric and antisymmetric linear combinations. Of course, here they're swapped around because, as I said, it depends on the parity, okay, of the underlying wave function. But this is the H2 plus ion, which is something you would have studied in QMA. I would have thought in quite a lot of detail by sort of maybe applying some finite well type behavior to it. So that's nice. So what does that actually boil down to? That boils down to a load of full energy levels, molecular levels, up to what we term the highest occupied molecular orbital, which corresponds to the pi bonding linear combination symmetric. Then there's some kind of energy gap, and the next available level is called the lowest unoccupied molecular orbital, pi star, which is the antisymmetric linear combination. And they're sort of EV sized, and you can define things like an electron affinity, which is the location of the LUMO below the vacuum level. You can define something like an ionization potential, which is the location of the HOMO below the vacuum level. And what is actually absolutely necessary, and we'll see that, is that we have some vibrational structure. In fact, the vibrational structure makes everything work. If we just had these single delta function levels, then you'll see that a lot of these devices wouldn't work. But the fact is, these are complicated molecules. They have a variety of omegas, vibrational omegas, if you want. They also, you can have rotation around single bonds. So effectively, what we have is a continuum of states sitting on top of these electronic levels. And I've considered a sort of the simplest possible HOMO, a twofold degenerate, one spin up, one spin down electrons sitting in the same. So this would be, these are one electron from each carbon, right? That forms this kind of double carbon-carbon bond. Okay, so that's nice. We've established that we can kind of mimic the electronics. We have a load of full levels up to the HOMO, and then an energy gap, and then a bunch of empty levels above it. And so we can imagine these full levels below to behave like our valence band, and these empty levels above to behave like our conduction band. And as I said, I've superimposed some vibrational and rotational levels in there to tell me that I've got actually almost a continuum of states sitting on top of each one of these levels. Right. I'll get this to. Oh, okay. Now I want to talk a little bit about delocalization length or conjugation length, because one of the things I said was that with these single double bonds, I can swap them around without breaking the chemistry. So I take this double bond, bring it here, take that one, bring it there, and take that one, bring it there. And in fact, we know that because when we draw something like a benzene, we draw a circle to tell us that really the electrons are delocalized within a site. So what I'm saying is we have a number of delocalized electrons within some kind of delocalization length or conjugation length within some region where they're quite happily sitting there like particles in a box. Okay, and then of course we'd expect a wave function to decay sort of exponentially away from this delocalization length. And for small molecules, you can say, well, the delocalization length can be one of these cores, such as in the far left, the LQ3, or again for the sort of for the polymers, it becomes a bit trickier because you could take it to be a monomer, or if these monomers are lying in plane, you could take it to be more than one monomer. Okay, and you could even begin imagining that you would have a distribution of delocalization length and therefore some kind of energetic disorder in these systems. I'm not going to talk too much about the energetic disorder of these systems. They're highly disordered systems. Okay, so we tend to work with Gaussian or near Gaussian densities of states within these systems where we consider the available sites and the available energetics for these electrons. But let's stick to the kind of cartoon here where we've got, so here is some delocalization length. These electrons sit in here, and then they only sit in here delocalized, and then their probability decays exponentially as we move away from this from this location, this delocalization length, maybe a monomer, or maybe a small molecule core, or maybe a sort of a part of a polymer. So how are we going to get from one place to the other? Because these electrons need to be able to move, right? Well, in the bottom right-hand corner, I've drawn a little cartoon. I've drawn a delocalization length site I and a delocalized site J. Okay, well, we know that in a classically forbidden region, we have an extinction coefficient determined by the energy of a particle. So there'll be some extinction coefficient of the wave function in here that's determined by the energy. And we know that the tunneling probability basically drops off exponentially. Okay, so if I were to place something here, and now you can see why we need these vibrational levels. If we can place a charge here, it could tunnel across from site J to site L quite happily, find an available level, they'll have to couple to the vibration and then thermalize. And so a downwards hop is always possible with an exponentially decaying probability with distance. So where I've written the Miller-Abrahams hopping rate, I've actually started with the second row first because it's easier to understand. If, however, we start off in site I and we want to move to site J, well, all is not lost because we know that the probability of occupation of site J is a simple Boltzmann probability of occupation. It's e to the minus ej over kt divided by some partition function. Therefore, the probabilities of occupation are, for some reason I've gone k and I, it doesn't matter. We just have to pay a Boltzmann price with the energy difference, which means if I start off here, with a Boltzmann probability, I can find myself excited to this vibrational level, which it actually matches up my site J. So I can still hop up, but if I hop up, as we can see in the first row of the Miller-Abrahams hopping rate, I'm paying a price, ne to the minus delta E over kt for upwards hops, and no price for a downwards hop, except I still have this kind of exponentially decaying kind of probability, which has to do with the separation between these sites. Okay, I'm modeling them very simply as just simple wells. So I think I've explained everything except this mysterious factor nu naught. So if I'm looking at the rate Kij, which is the hopping rate, the rate at which I try to hop from site I to site J, and it depends on the energetics, and it depends on the spacings, and it depends on my extinction coefficient. What is this nu naught? So this nu naught is the attempt frequency. And there are all sorts of complex ways of working out what an attempt frequency is. But what I'd like to tell you is that actually it's not so crazy, because we notice that for a downwards hop, I need to couple to some kind of vibrational state. Okay, so really I can immediately put an upper limit on this attempt frequency, because this frequency should have something to do with this frequency of that oscillation. So what I'm saying is, even though a lot of people might use it as a sort of free parameter, or there are quite complicated ways of calculating this attempt frequency, where we put a particle in a well and we let it bounce back and forth and so on and so forth. What I'm saying is, well, actually, we shouldn't be surprised that there's an upper limit to this, because we are trying to couple to vibrations. In fact, you need this electronic vibrational coupling for hopping to happen. So we've got charges within a site, and within a site we have this nice energy gap and this electron volt size, and this energy gap separates fully occupied levels up to the highest occupied molecular orbital. Orbital is just chemistry speak for wave function, right? And then we have this energy gap, and then we have the lowest unoccupied molecular orbital, which is just chemistry speak for lowest unoccupied wave function, right? But these are molecular wave functions, they're not atomic. So I can do my electronics on a given site, and I can move my charges from site to site thanks to tunneling and thermal activation. Okay, so another way of viewing hopping transport, if you want, is to say, well, hopping transport is really thermally activated tunneling. And the first row of the Miller-Abrahams hopping rate describes exactly that. It's got some raw attempt frequency nu naught, some e to the minus beta L. Beta will be something like 2 kappas, right? Multiplied by an e to the minus delta E, Ej minus Ek over kt, right? So we're paying these prices, and so it's strongly thermally activated. In fact, it's extremely strongly thermally activated, because what I'm not going to talk about today, but is very important, is the fact that these sites are disordered energetically and positionally. These are highly disordered systems, and therefore that really drives up the thermal activation of these devices. So what I'm trying to say is, if we look at our traditional kind of undergraduate picture of band transport in an inorganic semiconductor, we've got a valence band separated by an electron volt gap from the conduction band. We've got high mobility in the traditional inorganic kind of semiconductors. And because the mobility is limited by scattering process, the mobility would drop as we increase the temperature. Okay. The scattering rate goes up. In hopping transport, so in the kind of transport that we get in organics, the charges aren't delocalized within a bulk. So, you know, in band transport, in inorganics, you might talk about block orbitals, block wave functions, highly delocalized electrons, right? In hopping transport in organics, well, you don't have block orbitals. You have charges delocalized within one site, and the way they move from site to site is by hopping, and therefore you tend to have lower mobilities, but you tend to have this very strong thermal activation. Mobility goes up as the temperature goes up. And the picture we draw, which looks like the picture on the left, is to think of a HOMO with a couple of electrons in it, one spin up, one spin down, some vibrational structure separated by a LUMO, which also has some vibrational structure. And as a reminder to everybody, I define the mobility simply, if you want, it's the drift velocity normalized to the electric field. So I'm saying the drift velocity of a charge is the mobility times the electric field. Okay, so it's a way of just really figuring out how fast these things will move. Why do we need a mobility? We need a mobility because if we're going to make an electronic device, we're going to make a semiconductor device, we've got to draw some kind of code, right? So these charges have got to be able to move. So just like in your conventional semiconductors, a full valence band and empty conduction band will not give rise to a current, and we somehow either have to dope some charges up into the conduction or in the valence, or thermally activate them by heating it up, right? So again, we've got an e to the minus delta E over kT probability of finding ourselves above. So, right, we can do electronics. So that's cool, we can do electronics. What kind of electronics? Well, let's start off with the simplest possible device. Okay, the simplest possible device consists of an anode on the left-hand side, and I've denoted its work function, phi anode, and because it's an anode, we expect to have a large work function. Then we have some kind of organic semiconductor, which consists of sites, a bunch of HOMOs, a bunch of LUMOs, separated by an energy gap, which is electron volt size. And then we have some kind of cathode, and the cathode tends to have a small work function. Okay, so we've got an asymmetry, so already we predict that what I'm building here is a little diode, actually, and you'll see how these kind of diode structures are very useful. And the asymmetry here is not a traditional PN diode where we have a doped material, because these organics tend to be used in an intrinsic form. The asymmetry here comes because we've used different electrode materials. So in that sense, it looks like a Schottky diode in inorganic electronics. So in inorganic electronics, again, you'd use different electrodes next to a doped conventional semiconductor, maybe some silicon carbide or something, or some silicon or whatever, and then your asymmetry is built by virtue of your electrodes. So here's the open circuit energy position schematic. The dotted line at the top is the vacuum level. And if I were to short this, if I were to take a wire and connect my cathode to my anode, what would happen is the Fermi levels would equalize. Then that makes sense. It's a bit like connecting two containers, one which is very full with water and one which is less full. The thing is that the Fermi levels will equalize. And what we realize is that in the short circuit energy position schematic, the anode will find itself negative, the cathode will find itself positive compared to the vacuum level, and there is some built-in potential, and that built-in potential I've denoted VBI actually is to a first approximation of the difference between the anode and cathode work functions. That means there's an inbuilt electric field, okay, in my device, and that means we can do interesting electronics. So let's put a reverse bias into our across our device. So what we're doing is we're taking the cathode and we're making it even more positive, right? And really nothing's going to happen. Why? Because these electrons that are sitting at the Fermi level of the cathode cannot overcome the energetic barrier to enter the LUMOs. Likewise, they cannot enter the HOMO levels because they're fully occupied, right? And these are fermions, so they obey the Pauli exclusion principle. Likewise, if we look at these electrons on the left next to the anode, again, it's pointing the wrong way. These electrons cannot escape into the anode, i.e. we can't get a hold being injected because the Fermi level of the anode is sitting above the HOMO level of the molecule. So basically, if we put a reverse bias which is small, we're not going to get much of a current. Okay, let's now consider something like a forward bias. Well, if I put a small forward bias from the short circuit case, I start off with my short circuit case, 0 volts between my anode and cathode, and I apply a small forward bias. That means I make my cathode negative or my anode positive. What happens is, at some point when I apply the same voltage as the built-in voltage, I'm going to end up with what is known as the flat band condition. Okay, the flat band situation where I completely flatten down my band. Bands, I mean, they're not bands because they're discrete states, HOMO and LUMO levels, but you know, we borrow a lot of the language of conventional electronics, of conventional solid-state physics in this field, and for very good reasons, because we all have to take undergraduate courses in solid-state physics. So we are familiar with them, and so nothing much is going to happen. What's interesting is if we make our applied bias big, right, bigger than the built-in potential, then at some point, you see, we're going to tilt the levels the other way, which means these electrons from my cathode Fermi level can tunnel across into these available states. So we can inject electrons. Likewise, these electrons here from the HOMOs can tunnel across into the vacant levels of our anode, which is the same as injecting a hole. Which means now I've got an electron within the LUMOs, and this is mobile. It can quite happily hop downhill towards the anode. So the electron is going to leave the cathode and go towards the anode. Likewise, the hole, well, the hole is just the absence of an electron, so the hole is going to hop upwards, i.e. this electron in the next level is going to hop down. Thus my vacancy, well, it's not a vacancy, it's a hole, it's a missing electron from the wave function, is going to bubble upwards quite happily and hop. So my negative charges, if you want, go from cathode to anode. My positive charges, the absence of an electron, are going to go from anode to cathode. And really both of these processes correspond to what? They correspond to a conventional current going from anode to cathode. So what we've built here is a diode. Okay, and we've built a diode very simply by, I mean, it's the simplest possible device I can think of. 2 electrodes of different work functions with some kind of semiconductor between them. And then depending on how I bias these, if I reverse bias it, that is, I bias my anode negative relative to the cathode, or I bias my cathode positive relative to the anode, nothing happens. If I forward bias it, I bias my cathode negative relative to the anode, or I bias my anode positive relative to the cathode, then we get a current. Okay, so I started off talking about OLEDs, and I showed you all those pretty pictures of nice tellies and devices and smartphones and so on. And these are all OLEDs, and these days you get organic LEDs, you get PLEDs, which are the polymer LEDs, you get QLEDs, which use quantum dots to get some very narrow emission spectrum kind of emission. But anyway, let's start off with a very simple device. We're going to have some kind of transparent substrate, glass, typically. You need some kind of transparent, well, at least one transparent electrode, right, to let the light out. The stuff that's commercially used is indium tin oxide. Interesting, the indium tin oxide, which traditionally has been used as a transparent electrode for things like, you know, liquid crystal displays and so on. The whole display industry has meant that the price of indium has skyrocketed. So there's some really nice work which we're doing right now, actually, at Queen Mary. So Professor Gillen's working with an outfit called Paragraph, where instead of using indium tin oxide, they use sort of very thin sheets of graphene, okay, which are thin enough to be transparent and yet conductive enough to make a device. But I digress. Anyway, we have an anode. Typically, it's transparent. Then we've got some kind of organic semiconductor. Then we've got cathode, and that will be a low work function material, aluminium, calcium, something like that. And what we do is we bias the cathode negatively with my battery and the anode positively, i.e. we forward bias it. And what happens there is we get electron injection, we get hole injection, and these guys drift under the action of the electric field. And then what happens is Well, I mean, one's a positive charge and one's a negative charge. Therefore, they're going to feel a Coulombic attraction. And they can form a bound state known as an exton. I'm not going to go into the heavy physics of extons and the spin states because I really don't think I've got enough time. But you can see how this exton could quite happily recombine, right? This electron can drop into the hole. You can recombine with a hole in the HOMO, and conservation of energy dictates that it's going to spit out some energy, and this energy is going to appear as a photon, and the photon color, the wavelength, if you want, the energy is going to be dictated by that band gap. And since we're forming these chemically, the chemists can tune these colors just by altering the chemistry, right? By altering the exact spacing of my HOMOs and LUMOs. So it's all very, very, very simple, right? Well, the naughty kind of version that I'm giving you today. But the principles all apply. So that's nice. We can make an LED, and I'm not going to really talk about photovoltaics and transistors. I mean, I can some other time, but really, I think, given the time limitations, I'm not going to go into them. I did talk about detectors, though. That was in my title. So I'm going to talk about an organic photodiode. And one thing we noticed, first thing we noticed about this organic photodiode is it looks exactly like an LED, right? They have a substrate, an anode, an organic semiconductor, and a cathode. So what's changed? Well, actually, what's changed, if you notice the battery on the bottom right-hand corner, is I've now reverse biased it. I have now made my cathode positive and my anode negative. So basically, I take my diode, the same as my light-emitting diode, and I reverse bias it. Well, it's going to be under reverse bias, which means I'm not going to get a current, right? Well, okay, I'm not going to get a current unless, of course, I whack in a photon of the right energy to excite an electron from the HOMO up into the LUMO, right? If that happens and I absorb, well, then there is a probability that these guys will dissociate, that the electron-hole pair will dissociate before it recombines, and we could talk about probabilities of dissociation and so on, if we want to be really quantitative. But, you know, it was my deliberate choice to sort of try and cut out as much of the maths as possible for this talk. But as we can see, we can dissociate, and we're going to have a current. Now, notice the currents flowing the opposite way. The current's flowing from the cathode to the anode, the conventional current, if you want. The holes are moving to the left and the electrons to the right, which is the opposite way around to the LED, right? The driven LED. But it does mean that we now have a detector, right? We have a detector for photons in this example, and I want to spend the last 15 or 20 minutes of the talk talking about some detectors we've been doing. So some of the work we've been doing in the detector development group, which is an interesting collaboration between the condensed matter group and the particle physicists at Queen Mary, is that we are trying out some new applications for organic semiconductors. In particular, we're interested in radiation detection. Okay, so the particle physicists detect stuff, right? And this stuff that particle physicists detect, I call radiation, right? So one of the first jobs we try to do is to say, well, look, can we use these kind of organics to make something that instead of detecting light, it will detect radiation? Well, the answer is yes. This article has just been published maybe a month or two ago in ACS Applied Materials and Interfaces. I'm going to do the usual naughty thing. So I'm presenting this, and yes, I have a nice asterisk next to my name there because I'm the corresponding author. But you know, in reality, this work, the actual real hard work of this article, was done by other people. It was done by people like Frin Taifaku, Muhammad Ali, Joanna Borovic, Xiao Qi, Pete, Christian, Cosmin, Tamsin. So basically, as you can see, so Adrian Bevan's, well, you know, he's Professor Bevan and the head of the particle physics group, and myself, but I'm doing the usual naughty thing of presenting this work and saying, look at this beautiful work, and really I've done, well, I've written the paper, but I didn't do the actual lab work. Okay, the important people who did the real lab work are these people who were working towards their PhDs or the postdocs like Dr. Borovich. So let's have a look at the solution process. Donor acceptor of poly-3-hexyl-5 and phenyl C61 butyric acid methyl ester diodes for low voltage alpha particle detection. It's a bit of a mouthful, but basically it's an organic semiconductor alpha particle detector. So we use simple diode devices. So you'll recognize from my cartoon of diode that will have glass substrate, some kind of ITO anode, aluminium, and some organic in between. But actually, what we've done here is instead of using a single component organic, we've used what is known as a donor acceptor system. So the P3HT is the polythiophene, is that molecule that we saw kind of somewhere up here, I guess. This guy here. Okay, and the C60 is a fullerene. So there's a fullerene. So it's a football made out of 60 carbon atoms with a methyl group to make it soluble. And we've done this because what happens is if I excite an electron hole pair across either of these materials, then ripping it apart is energetically favorable. If there's an electron sitting in the LUMO of the P3HT, it'll quite happily drop to the PCBM LUMO and leaving the hole behind. Likewise, if I make an electron hole pair in the PCBM, the hole in the home of the PCBM will quite happily bubble up to the home of the P3HT. Do we have a question? No. Okay, that was someone tapping the microphone. So we have this, and this is called a donor acceptor system. So the P3HT would donate electrons to the acceptor, the fullerene, and we've done that really to maximize the probability of dissociation of these electron hole pairs, and we've mixed this up to give us plenty of interface, so that would happen. But otherwise, you can see we just have an aluminium cathode, it's on the left in this case, and a ITO anode on the right. So it's a simple, very simple device. And what we do with this very simple device, okay, well, the glass is several millimeters thick, so if we were to fire alphas through the glass side, we wouldn't get anywhere, right, because they wouldn't penetrate. But the aluminium, you see, you only need 50 to 100 nanometers of aluminium to make a very nice electrode. And the nice thing about 50 to 100 nanometers of aluminium is they hardly tickle the energy of the alphas. So if I take an americium source and I hold it near this device, these alphas will quite happily penetrate through the aluminium and into my device, into the actual semiconductor, the P3HT PCBM mixture. And what I can do is I can then take an IV characteristic. So what we have here is some series of IVs. I've written the modulus of the I simply so I can take the logarithm of something negative. Okay, so if you notice that's a logarithmic scale, so the forward current is bigger than the reverse current, so it is a diode, but I've taken the modulus of the current for anything negative simply because I can't take the logarithm of a negative number, right? It doesn't work mathematically. And what I do is if I take an IV with a current with the shutter closed, so no alphas, then take an IV with the shutter open, and then take an IV with the shutter closed, I can take the difference between the on IV and the average of two offs to give me a current enhancement. And that comes out as a function of voltage. And if I do this sort of 15 times over, I can calculate, first of all, my average current enhancement and evaluate some error bars, because I can look at the sort of distributions of the currents at any given voltage. Or I could average, you say I could average this matrix from top to bottom and then take the difference, or average across, taking the differences, so take the differences across and then average the bottom. But what it tells me is I can now have a current enhancement as a function of drive voltage with some reasonable statistics behind it. So let's look at the world's most boring plot on the left. So on the left at the top plot, we've got an IV for a device, which isn't even a very good diode. But what we notice is that in part B, we have the current enhancement due to alpha particle exposure as a function of voltage. And there, again, it's a bit boring because it's quite symmetric. but you know, it demonstrates that, and the error bars are quite small. They hardly poke out of our points in this particular example on the left. More interesting, much more interesting, is if we do this many times over for devices of different thickness. Okay, because that's kind of a bit boring, not much to say about that. So let's have a look at the sort of figure 4 on the right. What we've done is we plotted these delta I, these current enhancements, by alpha particle exposure versus a function of voltage, anywhere between -20 and +20 volts, for devices that go from thin devices, maybe 14 microns or 16 microns in plot A, going to thicker devices, maybe 19 or 25 microns in plot B, to thicker yet, maybe 45, 50 microns in plot C, to very thick devices, maybe 71 or 73 microns in plot D. And now it gets interesting, because what we notice is for thin devices, the forward bias enhancement tends to dominate. So we can see that, for example, in device 1 on plot B, the forward current enhancement is much bigger than the reverse. Likewise for both devices in plot A. And that's not the case for thicker devices. If I make thicker devices, the reverse bias enhancement dominates. So we can see this in plot C. If we look at the pink data points, they are, you know, remembering this logarithmic scale, right? They really are much higher in the negative voltages compared to the positive, and for both devices, actually in plot D, we notice that the forward response is frankly a bunch of noise, and the reverse response is actually quite good. Which got us thinking, I mean, isn't that interesting? The thickness matters. Okay, that's one way of measuring it. Now, excuse me, I could also do it in a much simpler way. I could just track the current versus time and just open my shutter and close it, right? And what we can see in these plots here is for one of these devices, we've done just that. We've fixed the voltage, and all we're doing is opening and closing the shutter, and you can see we get these nice steps in the current. Again, I'm plotting the modulus of the current because, for example, the top plot would be inverted, because it's a negative current, but you know, just to keep everything positive and sensible, we notice that we get this beautiful response. And in fact, this is an incredibly noisy response. These days, the signal to noise ratios we're getting for this kind of response is about 3,000 to 1, right? There's hardly any noise on it. It really does look like a step up. But you know, these are real results, warts and all. So there are two ways of measuring this kind of behavior. What we term the steady state, where we do an IV, and something which we call the time dynamic, where we do an I of t, and then we just basically jiggle the shutter, right? We open it at 30 seconds, we close it at 50 seconds, we open it again at 70 seconds, we close it at 90 seconds, we open it again at 110 seconds, we shut it at 130 seconds. Well, that's all very nice, and these two methods agree between them, and we get the same delta I by each method, so it's all very well behaved. But what about this weird thing with the thickness? Well, okay, I did say I was going to minimize the equations, but I couldn't really help this, because really, as any self-respecting physicist, I want a nice dimensionless figure of merit. In this case, I call it G phi, the gain efficiency product, for efficiency, right? And I've denoted as the alpha one, and I can calculate that. Well, all I have to do is apply conservation of energy in steady state, and I can relate the current enhancement to this G phi, to the electronic charge, an alpha flux, a number of alphas falling on our sample per second, and then the ratio of the alpha particle energy to the energy gap. Right, because the alpha particle is going to lose energy, and as it loses energy, it's going to excite electrons across the energy gap. Right, so I can define this product G phi in terms of things like, you know, how much does my current grow, what's the flux, what's the alpha particle energy, what's the band gap. And so if I were to plot this G phi, this nice dimensionless, self-respecting physicist, good measure, it's got no units, and it's just a pure number, versus thickness. for many samples. I can do that in red for forward bias, and I can do it in black for reverse bias. And what do I notice? I notice that for thin samples, the red points sit above the black points on average, i.e. the forward response is enhanced, but for thick samples, the situation is totally reversed. The forward bias response is far worse, more than a factor of 10 worse than the reverse bias response. And it doesn't matter whether I do it by steady state or time dynamic. In fact, here we've mixed all the data points together, mixed steady state, time dynamic. We know they're in agreement anyway, so we just made a large number of samples and measured these samples and calculated this gain efficiency product. And what we see is, I mean, this is at a fixed voltage, and in fact at a fixed electric field is even more dramatic than this, but I digress. And on the top, well, what's this thing on the top? Well, actually on the top what we've plotted is a modeled energy loss for an alpha particle versus position. Okay, modeled energy loss versus position. Okay, how'd you get that? Well, this is some stuff that Mohammed did for his PhD. Actually, he submitted his PhD, so he's now waiting for his Viva. But he used this Jam4 suite of software, and this allowed him to build realistic type devices where he put an organic semiconductor with a given stoichiometry and a given density and so on, and he could tailor his alpha source and the energy and so on and fire alphas at it, and then chop this into slices and look at the energy deposition for every size, and that allows him and allows us generally to plot the energy loss in MeV per millimeter versus position in the target. The target in this case is the organic semiconductor. And what we notice, and of course the integral of this is the total energy, right? Okay, so the integral of this energy loss versus position, it would be the energy. What he noticed is that for the 5.34 MeV alpha particles that come from our encapsulated source, these particles really, we've got a Bragg peak at 20-something microns and really don't penetrate any more than 25 microns. Okay, and of course you can do it for different energies. You can look at a alpha particle at americium that's not encapsulated, in which case you've got 5.49 MeV alphas coming out, and of course the range, if you want, increases to almost 35 microns. The Bragg peak shifts to the right. Now that's neat. That's very neat, right? Because that begins to explain to us why we would get this increase as we make the device thicker, up to a maximum at around 25 microns, and then a drop in the response. Because what it's telling us is that if I make my sample thin, then I'm only going to take a small fraction of the alpha particle energy in my organic, and the rest is going to be dumped on the substrate. So I would expect an increase in gain efficiency with thickness up until I've absorbed all the alpha particle energy. Now, problem with that is then I would expect this to go flat, right? I've got all the energy, therefore it should remain constant, which it kind of almost does for the reverse bias, but it certainly does not for the forward bias, which brings us to gain. Okay, what do we mean by gain? Well, I'm not presenting the results here because I realize I'm rapidly running out of time, but we know from other measurements that in these materials, holes are very mobile and electrons trap. So when I fire an alpha particle into this organic semiconductor, and I've got a sort of a forward bias case on the left and reverse bias case on the right, I'm going to make electron hole pairs, but the electrons trap. Now that does two things, and whereas the holes can quite happily whiz around, contribute to the current, you know, do their stuff. If the electrons trap, that makes the bulk of the semiconductor negative compared to the rest. That means that the bands are bent. The energy levels of the semiconductor are pushed up. Now, if I push these up, first of all, I reduce any injection barrier for holes. Secondly, I attract electrostatically holes, which means for every electron that I've got in here, a hole will come in, and on average, about 10 of these holes transit before this one hole recombines with that one electron, and we call that gain. Okay, we can get gain. So for each electron hole pair that we've generated, I can send through 10 holes on average before I recombine with my electron, which is pinned. And that will happen in forward bias more easily than in reverse bias, but it also happens in reverse bias. Well, that's all very nice, but what about this thing with the reverse bias switching direction? Well, see, the fact is we've got an asymmetry in our devices. We're always firing the alphas from the aluminium side because we cannot penetrate the glass that's sitting under the ITO, which means we're only ever generating these electron hole pairs where the alpha will go. If we make our sample significantly thicker than the Bragg peak, than the range, then we're not going to make any electron hole pairs near the ITO. We're not going to have any trapped electrons near the ITO. We're not going to allow the injection in forward bias, right? Because the injection in forward bias happens from the ITO. So that explains it. I increase my efficiency. My efficiency is slightly higher in forward bias. Why? Because it's easier to inject from the ITO. But if I make my device too thick, then I kill off any injection from the ITO. And so my gain, wallop, just collapses for thick devices. So by the time I've gone to 3 times the alpha particle range, I have essentially no response in forward bias, but my reverse survives. My reverse survives because I'm always making electron hole pairs next to my cathode. So even though originally it was harder to inject holes on the cathode, well, it is a cathode after all, actually for a thick device it doesn't care, and it stubbornly continues working. Right, a couple of minutes left. I've cobbled together some conclusions, which you may or may not sort of agree with. It was late, I was tired. So in conclusion, what I want to conclude from this talk, I want to say, well, commercial organic semiconductor devices based on all sorts of architectures, light emitting diodes, photodetectors, transistors, well, you can buy them, right? You can make them. The semiconductor nature of organic semiconductors comes via essentially the pi to pi star transition, the pi to pi star orbitals. They're easy to fabricate, and I've even called them a Schottky diode. To make a diode with an organic is a piece of cake. Regularly, my undergraduate project students, in the days when we were allowed in the lab, would make their own devices. Some of them would make very good devices. We can detect alpha particles. In fact, we can detect alpha particles with very low bias voltages, all sorts of advantages to this. We notice that the gain efficiency product will rise with device thickness up to the particle range, and if we make it too thick, then the reverse bias doesn't suffer, but the forward bias does. And that just about brings me to the end of the talk, and I'm more than happy to take questions. Thank you very much. And I can stop sharing. Do we have any questions? Hello?
Hi there. Thank you very much for doing that talk, Theo. That's brilliant. It was really interesting hearing about the work that you've done with that other team about for the alpha particle device. So, is that device then was it effective in what it had set out to do? Because you said there was a lot of noise in the data that you produced. So is it
okay, I see what you mean. So, okay, first thing I need to point out is whenever we publish, we're way out of date. So this work would have done a year before this thing got published. Actually, what we've done is we've moved forward. So these were really the first proof of principle type devices that we published. We have a very good team of people. We have one postgrad, Frini Taifaku, and we have one postdoc, Joanna Boroviec, and they're working as we speak on, I mean, first of all, the signal to noise ratios we're getting these days are hundreds of times higher, right? So we've really cleaned up our act. We've also discovered a lot of very interesting physics. I'd say that because I'm a geek, you know, okay, I mean, but some very interesting physics that underpin the performance of these devices, and the fact that, ironically, trapping, which was always considered the enemy, is not our enemy. It's actually our friend in this case. So yes, I mean, there are a couple of things, of course, to note, that this is just a proof of principle, right? All we're saying is, look, I mean, we can make these, and we can make them reasonably cheaply, and we can make them very easily. Literally, I mean, the fabrication is something that, you know, with an afternoon's training, anybody who's got any talent can build their own diode from scratch, right? But I mean, it's an ongoing piece of work. I think we've got about 3 or 4 different research strands now trying to improve on what was showed here.
Wow, thank you very much for answering that. Are there any other questions that anyone else has for Dr. Kreouzis before we end this talk? You can turn your microphones off, or you can post them in the chat and I can read them out for you. So we'll allow a few minutes for that. And so, what sort of things will these devices be useful for if in the coming future?
We have
the examples you gave in the start with the television screens and things like that.
No, we're not going to be making television screens. I mean, we have two studentships starting, 2 new students starting in, well, hopefully 2 new PhD students starting in September. One's going to be working on very large area radiation detectors. So very large area radiation detectors. So the kind of radiation detectors that you could possibly, say, use in an industrial process. Maybe you're decommissioning, so you pass your waste through some kind of portal, right? And then it says, this is radioactive waste, dispose of it that way, or this is fine, this is just rubbish, dispose of it as rubbish. So one project is kind of scaling up. Instead of making a device which is 4 millimeters squared, to make an array of devices that's maybe a square meter, right? So scaling up. Why? Because you can process these. You make them big. You saw how big that telly was, right? So going to meters squared is very interesting engineering, but it's essentially solved, right? So if I can write the specifications, I could go to a process engineer and say, right, here's the spec. Make this a meter squared for me. Make this 2 meters squared, and they will just do it. So that's one of the projects. The other project, it's something I didn't touch on today, because the other project is a slightly different architecture. So instead of making a diode for the detection, they make a transistor. Okay, and they use the similar mechanisms, but why a transistor? And actually the answer is because transistor is its own amplifier, right? So actually, to try and enhance the response of these devices by using a slightly different, I mean, really, we made it as simple as we could. Yeah, if it didn't have the 2 components, that would have been the simplest example I gave you, right? Just an anode and a cathode. So I mean, sometimes you have to be a bit incremental, but you know, we're thinking, well, we don't need to limit ourselves to sort of this kind of very simple architecture. We could, and at least one of the postgrads in the group now, he's no longer working actually on organics, but he's doing a PhD on thin silicon now. Sam Moss, he did a lot of work did last year as part of his MSci project. He did a lot of work in building these things into transistors and getting them to. But I didn't talk about transistors today because I only had an hour. Right.
Brilliant. Well, are there any questions from the group? Give you another few seconds to put those in the chat, or to please do unmute and ask Theo directly.
I mean, by the way, if any of you are interested in this kind of stuff, as I said, we're advertising at least 2 fully funded PhD positions in this field in the detector development group, and so if anyone's interested in applying for these, if you're in your final year and you expect to graduate, we do have some. I mean, these are fully funded positions, so they'll pay your fees and they'll pay your stipend. You know, they're not. It's all right. You know, you'll get paid to study. So we do have mean, one may have been filled. Well, I'm not sure. There are positions, there are funded positions available. So if you're at all interested in this kind of field, ping me an email. I'll show you the ads. I'll show you how to apply. If you just want to chat, we're okay. We've got a bit of money behind us, so it's not a bad position to be in. It's probably why I volunteered to give this talk. So, well, look, if any of you are graduating, let us know. So I've either bored everyone to tears or explained everything.
Well, I think I'd like to say thank you very much for delivering this talk. There's someone said everyone's saying the latter, and you've clearly done a very good job of explaining all of this, and it was incredibly interesting.
Oh, I'm delighted.
Yeah, thank you very much for your talk, Theo, for your time.
Not at all, not at all. A pleasure. And as I said, if you're interested, get in touch. If you have any friends who you think might be interested, who are sort of, graduating. These positions open in autumn of 21. So, we are open for applications. Pass it on.
Fantastic. Yeah, brilliant. Well, thank you very much for coming to this event as well. We are going to be uploading it onto YouTube. So tell anyone who missed it, who couldn't make it today, that it will be on our YouTube channel, which I did link in the email. And we hope to see you at the next event, which is, I know it's next
Thursday, isn't it?
It's Thursday, but I can't remember whose exactly it is.
David Berman interviewing Malcolm Perry.
The highly
Stephen Hawking, black holes and string theory. How could you forget? It'll be huge.
It will be.
6 o'clock.
Well, Dave Berman's a very good speaker, so
that
should be. What time is that on next Thursday?
6 o'clock, I think.
Oh, yes, I may even be able to make it. I may have even finished teaching by then. Excellent. Oh no, it's reading week.
Reading week, yeah.
Oh, great.
Lovely. Likewise for everyone else who's here, please do join us for that event. I'll just mention before we stop the recording, if you want to show your support for events like these, please do buy a membership on our QMSU page, so that we need money. We need money to run more events like this, and we've got an email came around saying that hopefully some on-campus activities will be happening in late March, stuff like that. So if we can, we'll be organising stuff like that.
Can I make a comment?
Absolutely.
To what you said? This is directed to the students. If you join the Student Society, there's some extra top-up money from the Students' Union, so it's not just your membership. If your Student Society grows, the budget grows with it. So it's not just your dues. It's actually a very helpful thing to the society, because then the Student Union budgets get set accordingly. So it's a very important thing to do. So join SciStar.